Good evening and welcome back to another class of data structures and algorithm. In today's session, we are going to discuss the asymptotic notations and time complexity. So basically the term asymptotic refers to the behavior of function or algorithm as the input size denoted as n grows infinitively large. So we have three types of, we mainly have three types of asymptotic notations. The first one is Big O which describes the upper bound or worst case complexity or worst case scenario. The other one is Big Omega describes the lower bound or best case complexity, best case scenario. And the third one is Big Theta which describes both the upper bound and lower bound representing the average case scenario. So today we will discuss all these notations one by one, and we'll also solve some problems of these notations. Basically, asymptotic analysis helps us to understand the efficiency of an algorithm as the input size becomes really large. It focuses on how the runtime or space requirements of an algorithm scale with the input size. Uh, while doing the asymptotic analysis, we generally ignore the constants and lower order terms. you will understand why we ignore the lower order terms. We only take the significant terms. So let's first talk about the Big O notations. Big O notation. Big O represents the upper bound of the running time of an algorithm, and thus gives us the and thus gives us the worst case complexity. Now suppose we have a function fn and a function gn. We use the expression fn less than equal to c dot gn. For Big O notation, this means that n becomes large, as n becomes large, the function fn will always be less than or equal to a constant multiple of some function. That means gn. Here gn represents here gn represents the upper bound of the function, the upper bound function, the upper bound function, the constant scales, the constant c scales gn upwards, ensuring that no matter how large n gets, our fn will never grow faster than c dot gn. So this defines the upper limit or worst case growth rate. So here in this diagram you can see that after the threshold value of n naught, our function fn is always smaller than the growth rate of the function fn is always smaller than the gn. Now the next notation is, we will cover some numerical problems on this which will make your concepts clear. The second one is, next we'll discuss big omega notation, which focuses on the lower bound and thus gives us the best case scenario for how fast an algorithm can run. we represents big omega using the expression Fn is greater than or equal to C dot multiple of Gn. This means no matter how large our n gets, the function Fn always be greater than or equal to a constant multiple of some function Gn. Here Gn represents here Gn represents the lower bound of the algorithm's performance. The constant C scales this constant C scales this function Fn downwards, ensuring that the function Fn never drops below Gn. So after this threshold value of n, which is n naught, you can see that Fn is always above the above this function Gn. So if we you know formally write the definition of omega for Fn to be omega of Gn, this is possible only if and only if there exists a positive constant C and n naught such that and n such that our Cn our C into Gn is less than equal to Fn for all n greater than equal to n naught, right? So we will also see the examples of this omega notation. The last one is theta notation. So this notation gives us a tighter bound by describing both the upper bound. This C2Gn represents the upper bound and lower bound of an algorithm. In big theta, we have two constants C1 and C2. These constants represent the lower and upper bounds of an algorithm's performance. The function Fn lies between these two bounds for all sufficiently large values of n. If we formally define theta notation, then we can say Fn is equal to theta of Gn if and only if there exist positive constants, there exist positive constants C1 and C2 such that C1 dot Gn. Fn lies between C1 dot Gn and C2 dot Gn for all n greater than or equal to this threshold value. So while solving the problem for theta notation, big O notation, we generally find the values of n naught and constant C1, C2. Now let's see some examples. So before coming to the example, let me summarize all these three notations. So we have big O notation, omega, and theta. This gives us worst case complexity, worst case performance, best case performance, and average case performance. In big O, we represent Fn as big O of Gn if there exists a positive constant C such that Fn is less than or equal to C dot Gn for all n greater than or equal to n naught. Similarly, for omega, we say that Fn is equal to omega Gn if there exists a constant C for which our Fn is greater than or equal to C dot Gn. For all n greater than or equal to n naught. And similarly, we say that Fn is equal to theta Gn if there exists a constant C1 and C2 such that our Fn lies between C1 dot Gn and C2 dot Gn for all n greater than equal to n naught. That means the threshold value. So now let's see some solved examples on big O notation. Okay, now assume that Fn is equal to 4n plus 20 and Gn is equal to n. So we have to find or prove whether is our Fn is big of Gn. So from the formal definition of big O notation, a function is said to be big of Gn if and only if Fn is less than equal to C dot Gn for all values of n where n is greater than or equal to n naught. That means we have to find the values of C and n naught for which this equation holds, this inequality holds. So we have to prove that for n plus 20 is less than, always less than or equal to C dot n. So let's choose the value of C as 5. Why 5? Because here I am taking this constant 5, one greater than this one, 4. Now let's check for which value of n and not uh, this inequality will hold. So let's make a table. 4n plus 20 and C dot n. For n is for C is equal to 5. We are taking C as 5. Let's check for n is equal to 5. This becomes 5 into 4, 20 plus 20, 40, and 5 into 5, 25. Let's take n is equal to 8. 32 plus 20, 52. And 8 into 5, 40. For n is equal to 10, this becomes 40 plus 20, 60, and this becomes 50. Similarly, going in this manner. So going in this similar manner, we can see that for n is equal to 20, these both expressions becomes equal. So we can say that for C is equal to 5 and n naught is equal to 20, our function Fn is equal to big O of Gn. For every value greater than or equal to n naught, this inequality holds. Now let's see another example. So the second question is prove that the running time of Tn is equal to n cube plus 15n plus 2 is big O of n cube. So We know by definition of Big O, a function fn is Big O of Gn if and only if there exists a constant c and n naught such that fn is equal to c dot gn for all values of n greater than equal to n naught. So this is what we are going to prove, that our n cube plus 15 n plus 2 this is our fn, and we say that it is always smaller than or equal to c dot gn. And what is our gn? Our gn is n cube, so that means it is less than equal to c dot n cube for some values of c and for all n greater than equal to n naught. So we have to find some n naught and c which satisfies this inequality. So if I from this equation, if I take n is equal to 1, then 1 plus 15 plus 2 should be less than equal to c dot 1. So from here we get that c should be greater than or equal to 18. So let's take c as 18 and n as 1. So for this values of c and n, our this inequalities hold, and we can say that our fn is the Big O of Gn. So hence proved. If you want to see, if you want to check whether our statement is correct or not, you can draw a table like this and can check for different values of n. Suppose these are the different values of n, and this is our n cube plus 15n plus 2 and 18 n cube. So if we put different values of like this here in this table, we will get 18, 40, 74, 126, 202, and here we'll get 18, 144, 486, 1152, 2250, and so on. So we can see for all n greater than equal to n naught, here our n naught is 1. Our this expression c1 dot g is greater than or equal to our fn. So we have proved our point. Now let's come to the next question. Okay, in the previous two questions, we were given the fn, the values of fn and gn, but sometimes we may be asked to find the upper bound for some function without giving the gn function. So in this case, what we will do, our fn is 3n plus 15. So our first step is to find the dominant term from this expression, which is equal to 3n. Uh, this is very intuitive why 3n is the dominant term, because for large values of n, for large n, this 15 will remain constant. Suppose I take n is equal to 1000, so 15 will be insignificant in front of 1000, 10,000, 1 lakh, like such type of values. So here in this equation, in this function, the dominant term is 3n. So what we'll do, we consider we take our gn as n. So as per the definition of Big O notation, a function fn can be written as Big O of gn if and only if fn can be represented as fn is less than equal to some constant multiplied by gn for all n greater than equal to the threshold value n naught. So here we have to find the values of c and n. So this our fn is 3n plus 15 will less than or equal to c dot n. So from this equation we have to find the value of c and n naught for this inequality holds. So here we can write this like this: c dot n minus 3n is greater than or equal to 15, or we can say that for n is equal to 1, c minus 3 should be greater than equal to 15. All this implies that c should be greater than or equal to 18. So for n is equal to 1 and c is equal to 18, this inequality holds, and therefore we can say that the upper bound for fn is on. Upper bound, we can say that upper bound for function fn is equal to 3n plus 15 is Big O of n for n is equal to 1 and c is equal to 18. Now let's see one more example. Sometimes you may be given such type of problem. We have to find the upper bound for this function fn. Here this function contains only a constant term 180. So assume our gn as 1, because as per the definition of Big O, uh, our fn can be written as Big O of gn if and only if there exists a constant c such that fn is less than equal to c dot gn. So I can clearly say that for C is equal to 180, our and n greater than equal to 1, our Fn will be always smaller than or equal to C dot Gn. So the upper bound for our function, the upper bound for function Fn is equal to 180 is equal to big O of 1 for C is equal to 150 and n C is equal to 180 and n naught is equal to 1. So now let's take some another example. We have to show that Fn is equal to 3n square plus 3n plus 3 is of the order of theta n square. This we have to prove. So as per the definition of theta notation, we say that a function Fn can be written as theta Gn if and only if there exist two variables C1 and C2 such that our Fn lies between C1 dot G1 and C2 dot C1 dot Gn and C2 dot Gn for n greater than or equal to n naught. So here we are covering, basically we'll divide here this equation into two forms. We have to prove that 3n square plus 3n plus 3 is less than or equal to C2 dot n square. Here n square is our Gn, and we have also to prove that our 3n square plus 3n plus 3 is greater than or equal to C1 dot n square. So we have to prove both of these inequalities separately and have to find the values of C1, C2 and n. Now let's solve them. Let's divide this whole inequality with n square. So this will become 3 plus 3 upon n plus 3 upon n square less than equal to C2. So if I choose n is equal to 1, our C2 should be greater than or equal to 9. Likewise here Also, let's do the same thing. Divide this inequality by n square. Then this becomes 3 plus 3 upon n plus 3 upon n square should be greater than or equal to C1. So I can say that C1 should be greater than equal to 3 plus 3 upon n plus 3 upon n square. I'm sorry, C1 should be less than or equal to 3 plus 3 plus 3. So if I choose n is equal to 1, C1 should be less than equal to 9. So what can be the smallest value that satisfies this inequality? Let's choose C1 as 1 and let's choose C2 as 9 for n is equal to 1. So I can say that for all n greater than equal to 1 and C2 is equal to 9, this equation holds, this inequality holds. This holds, and here for C1 is equal to 1 and n is equal to 1, our this inequality holds. So I can say that our this equation Fn is of the order of theta n square. This proves this proves that our function Fn is equal to theta of the order of theta n square. So like this, various questions on the asymptotic notations like big O, big theta, big omega can be asked in the exams. So before closing, let me summarize what we have covered so far. So basically in this chapter we have covered the asymptotic notations. Asymptotic notations are basically the mathematical notations used to describe the running time of an algorithm. We have studied three asymptotic notations. There are actually five asymptotic notations. There exist two more asymptotic notations, little o and little omega, but they are not very popular. So our main asymptotic notations are big O, omega, and theta. This we have covered. Big O notation represents the upper bound of the running time of an algorithm, and in most of the times we use the big O notation because we are only concerned with the worst case complexity of the problem. Omega notation gives us the lower bound or the best case complexity, while the theta notation gives us the average case complexity. Now let's talk about the common complexities available. We say big O1. This represents the constant time complexity. Then after this comes big O, log n, logarithmic time. This is much faster for large input. After this comes linear time. After linear time, we have big O n into log n. This is for this complexity comes for lookups in binary search. We found this type of complexity, linear search. This complexity we get with the merge sort and the best case of quick sort. We can also have quadratic time complexity. Time complexity which we get with the bubble sort and selection sort. Similarly, we can have exponential time complexity, and we can also have factorial times. Now if I draw a graph of above complexities like this, in the x-axis if I take the input n, and in the y-axis if I take time, then our constant time goes like this. Our logarithmic time, this is O1, our logarithmic time will be slightly like this, log n. Then our linear time will be at the 45-degree angle. This is our n log n, then n square, then exponential time, factorial time, like this. So time complexity analysis plays a vital role in the algorithm performance, and in almost all competitive programming examination, time complexities are asked. So this is a very important topic that we have covered today, and I hope that this video will definitely clears your doubt regarding the time complexity of an algorithm. Thank you very much. See you in the next video.